I'll hit record button this time. So this problem Noah asked me just this afternoon, and I haven't read this before. So I read on it, and then I thought, oh, this is easy because I've seen it many times before. And I did it, and I didn't realize that something was not the same as what I know. So anyway, it was just a relatively short fix. Once I realized it wasn't the same problem as I was trying to solve. Anyway, okay, so here it is. It says that you have a sequence of positive rational numbers, and rational numbers, of course, are numbers that can be expressed as fraction. P over Q in this case, where P and Q have no common divisors. So it says the infinite binary tree, full binary tree, labeled by positive rational numbers is defined by the following. First of all, the roots is 1 over 1, so it's the number 1. And then if you have a node that is P over Q, then the left child has the same denominator, but the numerator becomes bigger. Right, so the numerator is P plus Q. Okay. And then if you look at the right child is P plus Q over Q. So somehow, when you have this tree, so here you have 1 over 1 is the root. And then when you add the top and bottom together and replace the denominator, so you get 1 over 2. Or you can replace the numerator, you get 2 over 1. That's your right child. And then let's look at 2, 1. If you replace the denominator, 2 plus 1 is 3, so it's 2/3. And on the right child, you replace the numerator is 3 over 1. And one of the things that, I don't know, did it tell you this? Doesn't really tell you this completely, but it turns out that every single positive rational number will eventually appear in this tree. Okay. There's some theorem that explains why that is, but that's not important for this problem. You just have to believe that I give you any rational number, it will somewhere appear in this tree.
I think,
okay. Yes.
I think theorems like this are used to show that the rational numbers are countably infinite.
No, this is not the one.
It's something similar to this then.
No, I think you're thinking about slightly different proof. Okay, so I'm digressing here, but since this is still only just the 3 of us here, doesn't matter. So anyway, so I'm digressing here, but might as well. So to prove that rational numbers are countable, so you put, let's say, I don't know, numerator here and denominator here, and they just, let's say 1, 2, 3, 4. We'll just look at all the positive ones. And then you basically have an infinite grid. If I can draw these grids properly. And the idea is that you number these things in this way. So 1, and then 2, 3, 4, 5, 6, like that. So what does that mean? That means if you're counting the rational numbers, the 15th rational number is 5 over 1. No, 1 over 5, sorry. Or the 12th rational number is 4 over 2. Now, I'm not taking care of the fact that 4 over 2 is actually the same as 2 over 1. So actually, in this case, I have to skip the 12 and move the 12 over here. But anyway, that's the proof that you're probably thinking about. Is that the proof that you're thinking about to say that rational numbers are countable?
I think so, yes.
Okay. So it's true that this. So what is true? What is true is that if you believe that every single rational number is listed in this tree somewhere, then that's a different proof that rational numbers are countable, because you directly basically directly map every rational number to an integer index, right? So that's basically that's basically a bijection from natural numbers 1 to 2, 3 up to infinity to a rational number, a unique rational number, right? But anyway, there's no proof that that every rational number will appear somewhere in this list, and there's no proof that you cannot have the same number popping up twice, at least in this problem. Of course, it turns out that this is all true. But anyway, that's beyond the scope of this problem. But anyway, what they're saying is that you label these nodes. The first, the root is labeled 1. Then the next level is labeled 2 and 3. Then the next levels are 4, 5, 6, and 7. So every level, the nodes are labeled from left to right, starting from 1 at the top, and then 2, 3, 4, 5, and so on. So they even show you f of 1. The first one is 1 over 1. Then the second one is 1 over 2. Then 2 over 1. Then 1 over 3. 3 over 2. 2 over 3. 3 over 1, etc. Okay. So that's basically how you would take an integer and I guess convert it to a fraction. You could, at least theoretically, build this tree and then just look for the entry of the number that you want. Okay, now what is the problem? The problem, first line of input contains a single integer p, which is the number of data sets to follow. Okay, so that's just the number of cases. Each data set should be processed identically and independently. Okay, each data set consists of a single line of inputs. It contains a data set number k. Okay, a single space, the numerator p, a /, and then the denominator q of the desired fraction. What is it that you're supposed to output? For each data set, there's a single line of output that contains a data set number k, which is the first number in each input, followed by single space, which is then followed by the value of n, for which f of n is p over q. So in other words, I need to find in this sequence, in this tree, if I were to look at it one level at a time and start counting, which one is it that will give me p over q? That's the question. Okay. And because they did never tell you what if the answer is impossible, then you can assume that the answer is always possible. There's whatever fraction they give you, there's always an answer. The only thing that they'll say is that inputs will be chosen so that the index n you produce will fit in a 32-bit integer. Okay, so that's the problem. Before I go on to explain what to do, any questions about what the problem is asking? Okay. All right, so then let's look at, okay, let's look at this. So I have some node here, which is p over q. And on the left, it's going to be p plus q. And on the right, it's going to be p plus q over q. And then it goes on forever, infinite. Okay. You also know that you have a tree, a binary tree that's infinite. And there's some kind of numbering of these nodes. And what's the numbering of these nodes? The numbering of these nodes is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. Okay. Now, I don't know when you have learned, or maybe you have learned this or not in data structures and algorithms and so on. You might have heard of the data structure heap, a binary heap, actually. Does anybody not know what a binary heap is?
I think I've heard the name heap, but
You've never seen it?
I don't think so.
Okay, yeah, okay, so I wasn't sure because I don't know what people have learned from different people, but anyway, so a binary heap, it's basically a complete binary tree like this, and the numbers, you store numbers in these nodes, and each number it's always going to be bigger than or equal to the two children, and whatever number you see, it's always bigger than the two children, but then there's nothing that says the left child is bigger than the right child, or the right child is bigger than the left child. The left and right are not ordered. And it turns out that if you store things this way, the maximum of everything, it's in the root of the tree. And then there are different things that you can do to insert items and delete the maximum. And basically, it is the underlying data structure for a priority queue. It allows you to easily find a maximum, allows you to add things, delete the maximum, etc., etc. Okay. If you've not seen this, then it doesn't really matter. But what I was trying to tell you is that the heap, it's also organized in a similar way. But why do I bring out this up is that when you have a heap, even though this looks like a binary tree, you actually never store it in a tree. You actually just store it in an array. I'm using one base here. You can easily adjust things for 0 base, doesn't really matter. And you store things in an array where the index of the array item, it's basically correspond to this numbering here. And one of the things that you learn if you have done programming with heap is that whatever a node is, if the node is at the index of a node is X, then the left child, it's always 2 times X, and the right child, it's always 2 times X plus 1. If you're using 0 base, then this has to be adjusted, but for 1 base, so and you can look at every single node here, right? Take 7. Left child is 14, right child is 15. 2 times 7, 2 times 7 plus 1. Take this node, right? 2 times 2 is 4. That's the left child. 2 times 2 plus 1 is the right child. So this formula always works. And then also, if you want, I don't think we need to worry about it for this problem, but if you have already the index of a node X and you want to know what the parent is, then just go X divided by 2. And when I write divide in this way, I mean integer division, right? So if I take any node, let's say 9 divided by 2, it's 4, and that's the parent. So even though you don't actually explicitly build a tree, you can, given any node, the index of any node, you can easily walk up and down the tree using this method by using this arithmetic. Does that make sense?
Yes, I think we were shown that the array storage of binary trees,
Okay.
but I've never seen the left child, right child thing. That's pretty cool.
Yeah, but it only works if you have a complete binary tree. If there are any gaps, if there are any holes, so I don't know, if some branches are missing, let's say this branch is missing, then nothing works, right? Because then things are missing and then you won't get this complete picture. Okay, so that's one of the, I guess it's not exactly what this question is asking for, but it's related because this is basically gives you the numbering of all the nodes in this infinite tree, and also tells you how you go from one node to its 2 children, or going from a node to its parent, and that's important. Okay, so that's the first ingredient you need to have if you want to solve this problem. Does that make sense?
Yep.
Okay, now what is the second ingredient? The second ingredient is to, let me just erase this bunch. I'll keep the left child, right child thing formulas on the left. The second part of this formula is to look at this relationship, right? what can be, if I'm at a node, I know that I can get to my parents from the index with x over 2, whatever index it is, I can divide by 2. But how do I get, I know how to go from a node to my left and right child in terms of the fractions, but how do I go back up? Well, the first thing to notice is that this is p divided by p plus q. So the numerator, it's definitely smaller than the denominator. And so this is less than 1. Okay. And what's the other option? The other option is if you're on the other side, you're now going to be bigger than 1 because p plus q, it's of course always going to be bigger than q because p and q are always at least 1. Okay. So now then the question is, how do I go if I know what is a fraction? So if I have, I don't know, let's call it a over b. If I have a over b and I want to know, if I go up to my parents, what is the fraction here? Well, the first thing that I do is I ask, it's a over b less than 1 or a over b bigger than 1. Because if a over b is less than 1, I am in the left, I'm the left child of my parents. Otherwise, I'm the right child of my parents. That's the first thing that you want to figure out. And then if you're the left child, you know that your denominator of the parents is exactly the same as what you have. Right? Because when you go down from here to here, the parents denominator hasn't changed. It's both p. What's changed is that you added p into the denominator. So what does that mean? That means that you say b minus a. You need to subtract the numerator to get back the original. Does that make sense?
Yes.
And you can do this, you can always do this without getting into trouble, because if a over b is less than 1, that means a is less than b. So b minus a, it's not going to give you a negative number or something strange like that. Okay. So now, what about the other way? If a less than b, if a greater than, sorry, if a over b is greater than 1, you're in the right child case. So in this case, the denominator is the one that's not changed. And the numerator, you have to remove the denominator like this. Does that make sense?
Yep.
Okay, so now if that makes sense, what are we going to do now? We're going to do this recursively. And so let's start. So you give me a number. You give me p over q. What am I going to do? I'm going to go up to find my parents. And I'm going to ask, what is your index? So what is the parent index? If I know what my parent index is, call it pi. And if I know that I'm a left child of my parents, then that means that my index, it's whatever my parents' index is times 2. If on the other hand, I'm the right child, then whatever my parent index is, my index is 2 times parent index plus 1. Okay, so that's kind of the main thing is you walk up the tree, you ask your parent, what is your index? Whatever you get out of that, you either multiply that by 2 or you multiply that by 2 plus 1, depending on whether you are the left or the right child of your parent. So how do you know your parents' index? Well, you recursively do this until eventually you get to the roots. Because when you get to the roots, you have 1 over 1, and the index is 1. You will always end up at the root eventually.
What's the running time of this?
Okay, let's yeah, okay, so I maybe maybe first thing is do you believe that this works assuming that this thing's even terminates? Right? I'm just telling
Oh,
you,
yes.
I'm just telling you that you will always end up at 1. Right? Are you just gonna believe me, or do you have to do I
Well,
need to prove it to you? Probably you should ask me to.
every node either has a parent or is the root node, and if you always get the next parent,
Yeah, but is that clear that you're not gonna somehow run in a circle? That somehow numbers kind of
oh,
yeah, who
trees
knows?
aren't cyclical.
Well, but
They don't
yeah,
contain
okay,
cycles.
but you're believing the description of the problem that this is a tree. I mean, there are
Oh,
things in
that's
the
true.
problem statement that they kind of you kind of read and assume, and you never really question, right? But anyway, I will answer your other question while I'm trying to prove to you that it's correct. But let's first let's say that do you agree with this algorithm that if it terminates, it will give you the right answer?
Yes.
Okay. So now the question is, do we know that it terminates? And if it terminates, how bad is it? Right? This is a big question. And the answer, it's actually that this doesn't take very long. Then you might say, well, how do you know this? Okay, so wait, where's my whiteboard? I was trying to do previous page. Where is it? Okay. So you have, so what's going on? If A is less than B, or in other words, if A over B is less than 1, or in other words, if A is less than B, what are you doing? You are replacing the bigger number with B minus A. Correct?
Yes.
And here, in this case, when A over B is greater than 1, what are you doing? You're replacing the bigger number with the difference of the two. Agreed?
Mhm.
Do you remember any algorithm where you do something in this way? Any well-known algorithm?
I think the GCD, but I only guess that because that's in your code that you showed me.
Well, that's a different thing, but it's true. So what does GCD? Did you clean an algorithm? Let's pick 2 numbers. If I want to compute a GCD of 2 numbers, which 2 numbers? Let's say what is a good number to choose? 60 and 24. Okay. So the Euclidean algorithm says usually 60 and then you mod 24, it's equals to 12. And then you kind of replace the big number with the 2 smaller number. And in this case, I guess it's not very interesting because we're done. So this is 12, yes?
Mhm.
And you know that Euclidean algorithm always terminates because the modulus that you're dividing by, it's getting smaller and smaller every step. And so, and then the modulus can never be less than 0. So it will eventually stop. Okay, but what is 60 mod 24? What does that actually mean? 60 mod 24, it's 24, 60 minus 24 times the quotient, right?
Mhm.
Of this, whatever that, I guess I should write it like this, the floor, which is 12. And in this case, it's 2. The quotient is 2. So you basically multiply 24 times 2. Okay, now what are we doing over here instead? We take 60 and 24. We're replacing the bigger one by the difference. So the difference is 36. Then we do it again and replace the bigger one by the difference, which is 12. What did we actually just do? we are basically doing division by repeated subtraction. Right, so if I'm dividing and instead of saying that I can divide, I can subtract 224 all in one step. I have to actually break it down into 2 steps. But ultimately, even though it's less efficient, it is the same thing. So, in other words, when you start from a number and you kind of walk up this tree, you are actually doing Euclidean algorithm. Maybe in a slower way, but it's basically Euclidean algorithm. Does that make sense? Okay, so the important thing is that basically you always take the larger of the 2 numbers and replace it by the difference. And so that's basically Euclidean algorithm. So then you would have to say, first of all, does it terminate? Does it always get to 1? The answer is yes, because it's a Euclidean algorithm. It will always eventually get to nothing. And then the other thing is, now that we know that it terminates, how long does it take to terminate? And Euclidean algorithm is actually very efficient, even though this time you're only subtracting sort of 1 step at a time, but it's still going to be very efficient, and it's basically logarithm. Basically, it's logarithmic in terms of number of digits. So it's big O of the number of digits in your inputs, which is not very big, of course. In this case, it's numbers are at most 32 bits, so basically big O of log of 32, big O of 32 or something like that. Does that make sense? Oh, I see we have Marcus and one more person joining. Okay, by the way, I did manage to hit the record button, I think. So hopefully my computer won't crash this time. I'm not turning on my second monitor, so hopefully I can post the recording. Okay, so that's this sort of bonus problem, I guess. It's
So what are you actually using the GCD algorithm for in your code?
I probably don't need it. It's for a save. I was doing it for something, and then at the end I don't think I needed it. So I'm using the GCD just to make sure that the number you gave me, it doesn't have common factors. Because I don't remember if the problem says that P over Q may or may not have common factors. It doesn't say it. So it doesn't say that P over Q in the lowest terms. So I just wanted to divide that out just in case. That's all I'm using it for.
Does it just make it faster, or does it just
well, okay, so that's the problem is at some point yeah, so okay, in fact I don't think it matters the way that I wrote it at the end. If I were to check that P and Q are both 1, then it matters, because it could be 5 over 5 as opposed to 1 over 1.
I see.
But because at the end I just do it like this. So let me just get rid of this and resubmit and see if it still works. I think it's okay actually. Okay, I just resubmitted this, right? Oh yeah, it works. Yeah, so I actually didn't even need this. I was doing it the other way when I was solving the wrong problem, and then I just left it in.
I see.
Okay, anyway, I said I was going to talk about the Google.
So
Yeah.
you can't check if they're both equal to 1. That doesn't work. You have to check if they're equal to each other.
I think it's safer to do that because there's no guarantee that the input won't be 5/5.
I
Right?
I believe you left it as P equals Q.
Yeah, so but if I write P equals to 1 and Q equals to 1, and somebody put in 5/5, then I might be in trouble. Because now I will never reach base case. So let's see what happens actually. I'll be in trouble because I might be dividing myself. Oh, maybe there's no such input. If there's input like 5/5, I'm in trouble. But I guess there isn't.
I see.
Okay. Anyway, I guess that was you call it defensive programming,
Mhm.
just in case. All right. So what I said I want to talk about is Google Code Jam this past year, round 1A. And what is this round over? Oh, I see. So I did this and I did 2.5 problems. I didn't get the actually I didn't even bother doing it, to be honest. And I figured I wasn't good enough, and I did. I think it was the top 500 can advance, so I advanced to round 2, which I did horribly, but that's a different story. All right, so let's look at these problems here. This is meant to be the easiest one, and I did it in 6 minutes. So let's read the problem. You're given a string of uppercase English letters. You can highlight any number of the letters, possibly all or none of them. The highlighted letters do not need to be consecutive. Then a new string is produced by processing letters from left to right. Non-highlighted letters are appended once to the new string, while highlighted letters are appended twice. In other words, anything that you highlight are doubled up. Okay, that's another way to look at it. So for example, if the initial string hello world, you could highlight H and then L, first L, last L, and the O. And then when you actually get the string after you double things up, anything that is highlighted becomes duplicated, and things that are not highlighted just by itself. Okay, that's the question. That's the operation. Notice how each occurrence of the same letter can be highlighted independently. So even though there are 2 L's here, one of them is highlighted once, and then the other one is not highlighted at all. So you get 3 L's. Okay, given a string, there are multiple strings that can be obtained as a result of this process. Depending on the highlighting choices, among all those strings, output the one that appears first in alphabetical order, also known as lexicographical. Okay, so basically you have to say, okay, let's look at all the possible ways of highlighting letters. For each one, you can figure out what the resulting string is by doubling up the highlighted characters. And out of all those possible strings, pick the one that is smallest lexicographically. Okay, that's the question. Note, a string S appears before a different string T in alphabetical order if S is a prefix of T, or if the first place S and T differ, the letter in S is earlier in the alphabet than the letter in T. Okay, so they're just defining what alphabetical order means, but that's basically string comparison order. Okay, so is there any question about what this question is asking? Right, they give you a string. So for example, here, peel. And out of all the possible ways you can decide to double things up, you want to find the one that is lexicographically smallest. So for example, they say in sample case 1, peel, all the strings that you can contain in alphabetical order are these. So this one has both of the E's doubled up. This one has both of these doubled up and then an L doubled up. This one only has one E doubled up, and so on and so forth. Okay, and you want the one that is alphabetically the first, no matter how you double it up, or you can decide not to double up at all. So in this case, in the second case, the string is how many A's? 10 A's together. And if you don't double anything up, then that turned out to be the first one, because any other string will have more A's, but they're still all A's, so they will come later. And then the last one, Code Jam Day, it says that in the case 3, there are 1,024 possible strings which can be generated, and out of all of that, this particular string is the one that is smallest. Okay, so that's the question. Are there any questions about what is being asked here? All right. So they tell you actually, so in the actual contest, you can do the 2 different test sets, and you get different points. If you solve if you only solve only one set but not both, you get partial points. If you solve both sets, you get all the points from this problem. It's 10 points if you solve test set 1, 15 points if you solve test set 2. During the contest, you see the answer, you see whether you got test set 1 right away, but you don't know until after the contest whether you solve test set 2. So that's what they mean by hidden visible versus hidden verdict. Okay, so test set 1 has string up to length 10, and test set 2 has strings up to length 100. Okay, so that's the question. Any ideas on how to approach this, even if you just want to know how to do, even if we just want to do the easy test sets with 10 characters? Any ideas? Marcus, okay. Marcus raised his hand. You want to say something?
You can go Noel if you want.
Oh, yes. I was just thinking a suffix array where the input is the string where you double every character, and then you pick the lexicographically, you pick the first one in the suffix array.
Well, the issue that you have is that, okay, so I don't know how many people know what a suffix array here, but the issue is that when you double up every character, you are now not allowing yourself to double, let's say, the first character, but not the second one. Your suffix array will not capture that, because suffix array only kind of works on the back end. So if you have double up every single character, then your last character is almost forced to be doubled if you double anything at all. Does that make sense? Okay, let me just very quickly write this down. So let's say your string is Peel, right? This is your string, this is your input, and you say, let's double everything up. That's the worst possible case, I guess. And then the suffix array, what suffix array does, if for people that don't know, it's it will take all the possible suffixes. So in this case, the suffixes are substrings that start somewhere and run all the way to the end, if you didn't know that. And then L. If I'm doing this by hand here, but I believe this is the suffix array, all the 8 suffixes sorted in order. Okay, so now how are you going to recover the correct answer? I guess that's the question. Right, you're correct. You might think that what you should do maybe is take this and then glue onto it what's in front that is not doubled up. Maybe that's what you're thinking. But the answer is the correct answer is actually this, not with the double L.
Oh, I see.
So that's what I mean when I said that once you decide to double up something, then you're forced to double everything else up after that. Okay. Marcus, you want to say something?
Yeah, so I honestly don't know what a suffix array is.
That's fine.
But how I was thinking is you would do it is you would just take it character by character, and if the next character was greater than the one that you have, then you would double the one that you have, so that it would be earlier. And if it wasn't, you just not double it, and you wouldn't double it if it was the same as the next character.
Okay, so
But
let's
if
try with this one. So you start one character at a time, you have a P. What are you gonna do?
you're gonna say that E is less than P, so you don't double that P.
Okay, and then,
And
so
then
now you look at the E. Now what do you do?
and you're not gonna double it because it's the same as the next.
Okay, and now the next E, what are you gonna do?
You're gonna double it because E is smaller than L.
Okay, and then the last character, you never double up.
Sure, let's go with that. I wasn't sure how to handle the last character.
Okay, okay, so is that the right answer? Let me just check. For this PE, no. It's 4 E's. Okay, so it turns out that it's better to double both E's. Because when you double both E's, then this E will be able to be smaller than that L.
So do you have to remember if one of the previous letters was equal to the current letter? And then double up the previous?
Okay, maybe.
And then with the same rules so that you can account for the A, right? Because
I mean, I know how I did it, so, but I want to see what you people think. Okay, what about the small case? Forget about the larger case for now. So the length is at most 10. Right, so you have 10, at most 10 letters. And let's make it really small, just to make it maybe even easier to think about. So let's say it's only 5, at most 5. Right, A, B, C, B, D, or something like that. Okay, so let's say that there are only at most 5 characters. What can you do? Well, the idea is that every letter, it's either highlighted or doubled or not. Right? It's either double or single, every one of them. So really, if you think about it this way, then every character, you have 2 choices. You either copy it by itself or you copy it doubled up. If you think about it this way, there are basically 5 choices. Each one has 5 positions. Each one has 2 choices. So the total number of possible choices of which ones to highlight, it's 2 to the 5, which is 32. And 32 is very small. So what could you do? In that case, you can just generate all possible 32 strings, right? Because basically it's every character you can decide to double up or not double up. You generate all 32 possible strings, store them into an array of strings, sort it, or find a minimum, whatever. There are many ways you can do this. With 32 strings, you don't really care how you do it because it's so small that just about anything you do will probably be fast enough. Okay, and then the actual problem doesn't say 5. It says 10 for the small case. Well, it's 2 to the 10. It's 1024, which is still pretty small. Right, so it's not really that big of a deal to actually just try them all. Does that make sense? Generate all of them and then either find a minimum out of the whole list or sort them or whatever. It doesn't matter. Does that make sense?
Yes.
yeah, but isn't that sort of a bad habit to get into? Because
Well,
I feel like you'll never be able to solve the larger cases if you get used to doing that.
well, I guess the question is, yeah, it depends on what your goal is. If you just want to solve the easier case, if you don't know how to, so obviously, if you know, when I was going through this contest in real time, I would never try to come up with just this and waste my time if I know how to solve the bigger case, right? So I look at the big case and I think about it. If I don't know what I'm doing with the big case, then I would do this just to get some partial points and then think about it maybe some more later. But you know, it's still good, at least then, you know, while we're doing this offline, not in a real contest, to think about, you know, different approaches. Okay. Okay, but obviously this is not going to work when you have the large case where the length is at most 100, because now you have 2 to the 100, which I'm not even going to attempt to write. There's no way you can try them all. Okay, so now what are we going to do? That's the question. Okay. Now, one of the things that you guys mentioned was that we go from left to right, and then for each character, you look at the next character and decide whether you double up the current one or the next one. But then what if you have multiple E's? And then maybe things gets a little bit complicated. Maybe it's not just 2 E's, maybe there's 3 E's in a row, and so on. And the problem is you need to look at the next one, but then sometimes you don't really want to look at the next one. You want to look at the next one that's actually different in some way. And it turns out that if you do it this way, it's actually not, maybe a little bit hard. Maybe you want to go the other way from right to left. Maybe that's easier. Okay. So let's think about if you go right to left. Okay, so the first letter, you can try to maybe just do L, or you can do LL. LL is obviously worse than L, but usually I think the last letter you never double. Okay, now you look at the E. E is now greater than L, less than L. So then you say you want to double that up, right? And then you say, well, what about the next E? Do I want to double it up or not? Do I want this one or do I want this one? And then you kind of say, well, now I have to kind of scan forward again to know that the last letter that's different is L, and L is greater than E, so you want to double it up, and then finally you see a P, and so on. So somehow you have to kind of remember what is the last letter, maybe the last 2 letters, in case you're seeing the same letter multiple times, which kind of a little bit hard to manage. Sometimes you look at the last character, sometimes you look at the last 2, or maybe the last 2 that are different or whatever. It seems a little bit tricky. Well, what to do? Well, at some point I just said, it didn't take me too long to decide that I'm not going to screw around with these intricate reasoning, because I didn't want to figure it out. How did I do it in 6 minutes without trying to figure this left and right and left, and last character, last 2 character, whatever? Okay, what do I do? Well, the first thing I'm going to do is I'm going to go from left to right. Okay, whatever string you give me, it doesn't really matter. Just a bunch of characters. Okay, I'm going to go 1 character at a time. Why do I go 1 character at a time? Because the dictionary order, it's defined from left to right. If I know that the left, it's smaller, okay, if I have P versus this, I know that this one is smaller regardless of what comes after. Okay, so I want to look at it from the left side. So what is my choice? My choice is that I either do P as a single or P as a double. Now, I'm not considering any other characters yet. Okay, all I'm looking at is whether I should double the P or not. And how would I know this? Well, we can say, well, if this next letter is less than P or whatever. But the problem with this approach, as we have seen, let's say we're considering this one. If we decide to expand this one into 2, if you just look at the next character, it's not so clear. You have to look further down to see that, to see where the difference is, because of the fact that you have a bunch of E's. So what do you do? How do you kind of take this into account without doing too much logic? Well, I don't know if you call it cheating. So what am I going to do? I'm just going to say, I want to do either this one or this one. Which one is better? Well, I'm just going to call one of them string 1 and one of them call string 2. And I'm just going to ask C++ or use standard string comparison and ask C++, tell me which one is better. If this one is smaller, then that means that I want to just use a single one. If S2 is smaller, I want to double it. And this less than operator with strings basically hide all the mess that you have to do, right? Because it basically look down the list as much as it needs to figure out an answer. And whatever I decide, once I decided that this is the way to go with a single one, I never have to look back again. I know that I do not want double P. I don't want this. I know I want single P. So from this point on, I only have to deal with the remainder of this string. And I repeat the same problem again. I repeat it as, what if I double up the next character or not? Which one is better? And so on and so forth. And basically I just repeatedly ask, what if I double up this character from that point to the, and while everything else is fixed? Is that good? Is that bad? And if it's good, then I double it up, otherwise I don't. And I just keep on moving. And you might say string comparison, isn't that expensive? You might have to compare the whole string. The answer is yes. This is an n-square algorithm, the way that I've described it, because I'm looping through every time I'm using string comparison, which is linear time. So altogether, it could be n squared where the length of the string is n, but n is 100, so who cares if it's n cubed or n, even n to the 4th. N squared is definitely good enough. So let me show you my code. Okay, so just like as I said, most of these CodeJam problem always starts with the same template. You read in the number of cases, then for each case, you print out a case label and then you solve each case. So that's what I do here. And here's my code. I'm doing lots of things that are not very efficient. Okay, so let's see. What do I do? First, I read the string. Okay, so that part is no surprise. Then I am going to build up my answer. So I'm going to start with my answer as an empty string. Then for each character from left to right, what am I doing? I first grab the substring of everything, okay, up from that point to the end. Okay, so that's basically saying, pretend that the previous loops already fixed the characters that before me. Temp is the string if I don't double up the current character. And temp2, it's I take temp and then I add an extra character in front. Okay, so I'm basically doubling things up. Normally, adding things to the front, it's very inefficient. Well, I should say it's always inefficient when you deal with strings and vectors and arrays. But again, I didn't really care because this is arrays of at most strings of at most 100 characters. Inefficient is not really a big deal. And then I just say, okay, if it is better to not double up, then I just add to my answer 1 copy of this character. Otherwise, I add 2 copies of this character. And then I just run through this loop and I just print the answer. That's it. Okay, so you might say that this is not the most elegant solution, and I would agree in terms of the, I guess, reasoning and so on. But maybe I would also argue that this is the most elegant solution. Well, I shouldn't say most. This is my most elegant solution if I want to get it done quickly, which is the point of what I was attempting to do. Okay, not necessarily the most efficient, but the quickest thing I can write that will be acceptable. Because 100, it's really not that much. I can do n squared, even n cubed within 2 seconds, no problem. Does that make sense?
Yep.
Okay. If you
Would
wanted to, sorry, if you
would-
wanted to, could you express this as recursion? That's your question. Yes, you could express this as recursion, sure. Basically, you would look at the first character, and then you decide whether to double up or not, and then you recurse on the remainder of you recurse on the substring of the string with the first letter taken off.
Cool. Thank you.
Yeah, so you can do that. That's not a huge difference. Okay, now this, yes. Anything?
Would Marcus's solution, if it worked, been faster?
Likely. So I think so let's see what they say actually in the analysis. They probably tell you so test set, okay, so what do they say? Test set 1, since the length is at most 10, the number of new strings you can obtain is at most 2 to the 10. So try them all. Okay, so that's basically what I said. And then here, now that the length is up to 100, this is too much to enumerate. Note that a string P appears before a different string Q in alphabetical order. If P, blah, 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 this is a definition of lexicograph. So for any SI, we have the following rule to decide if the next different character. So now you see, it's not if the next character, but if it's the next different character in S is lexicographically larger than the current letter, then we must highlight SI. If the next different character in S is smaller, then you must not. If there's no next character different, then we must not highlight. So then the question is, do you know how to get the next different character? And then there's a different ways you can do this. And one way is to actually scan backwards to figure this out. But then there's another way you can compress the string and so on. Okay, so the time complexity of this solution is bigger of S, the bigger of the length. So yes, if you do it more or less kind of what the linear scan, you can do it in bigger than linear time. And definitely much better than mine in terms of complexity. But I would argue that I don't have as much complexity in my brain when I was trying to solve this problem and try to move on to the next one. So yeah, mine is definitely inferior. It's n squared time, but it's faster for me to write. So sometimes you have to optimize depending on what you're trying to do, right? Do you want to optimize your algorithm, or do you want to optimize the time it takes for you to write the code? And for me, for most contests, you try to figure out what is the easiest thing that is acceptable. And in this case, the easiest thing that's acceptable for me was the quadratic algorithm, right? And I did it, 6 minutes, basically. Okay. Any more questions or comments? All right, the next problem is a fun one, I thought. And it's a quite different kind of problem. Okay, then this I kind of talked about maybe I say something about knapsack. This is somewhat knapsack, I don't know. Let's read. You're given a set of distinct integers. Okay, so you have a bunch of integers. They're all distinct. You need to separate them into 2 non-empty subsets such that each element belongs to exactly one of them, and the sum of all the elements of each subset is the same. So I give you a bunch of distinct numbers. You have to separate into 2 parts. They don't have to have the same numbers, the same number of numbers. Some can have maybe just a 1 and some have 5. But the important thing is that every number must appear either on one set or the other, and the sum of each subset has to be the same. And this is actually, there's a name for this. The name is actually got an equal sum problem, which is the title of the problem. And it says an anonymous tip told us that the problem above was unlikely to be solved in polynomial time or something like that. So we decided to change it. So if they didn't change it, if that's all you're given, a bunch of numbers you have to separate into 2 equal parts, that problem is what is called NP hard. And it's a problem that basically nobody knows how to solve quickly. If you know that the numbers have a finite range, have a small range, maybe that the integers are from 1 to 1,000 or something like that, and you have 1,000 of these numbers, then it turns out that you can use knapsack to solve this problem. But in general, if these numbers are big, and if you can have any integers you want, then this method doesn't work. So then they tell you that no, you can't, this is hard. So they're going to change the problem. Now you get to decide what half of the integers are. So I have to tell, so this is a kind of a strange problem. It's called interactive problem. I actually don't just take the inputs and then compute. I take some input, I send some output back. Then based on my output, it will send me some other input, and we can kind of go through multiple rounds. That's what's called an interactive problem. Okay, so an interactive problem with 3 phases. In phase 1, I give them n distinct integers. Okay, so I have to choose n distinct integers. In phase 2, they are going to give me n integers that are distinct from each other and from the ones you choose. So at the end of the day, you chose n integers, they give you n integers, all of them are different. In phase 3, you have to partition these 2 n integers, so n of them are from you, n of them are from them. You have to separate it into 2 subsets, both of which sum to the same amount. All the integers have to be between 1 and 1 billion inclusive, and it is guaranteed that they sum up to an even number, because if they don't, then there's no way you can separate them into 2 equal halves. Okay, so they tell you some input, so they tell you how to actually write this program though. So initially you read an integer t, which is the number of test cases. For each test case, first you read a line containing single integer n. This is, the judge will tell you n. Then you give them n distinct numbers called a1 up to an. Those are your numbers. Each of these numbers have to be between 1 and 1 billion. After that, you will be given n numbers, b1 to bn. All of these numbers are different. And then finally, your program must output a line containing between 1 and 2n minus 1 integers from among these 2n integers, the ones that are chosen to be part of the first subset. And anything, the integers from a and b that you do not output are considered to be part of the other subset. The next test case starts immediately if there's 1, blah, 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 and so on. So let's read this sample. So there are 2 test cases. First, the judge tells you 3. So there's 3 numbers. Well, there's 6 numbers. You give 3 of them. So you say, you tell them 5, 1, 3. The judge tells you 10, 4, 9. So now your set is the 6 numbers. And then you output 1, 10, 5, because 1 plus 10 plus 5 is 16, and it happens to be exactly half of this sum. And then there's another problem. It's 3. Again, you give 5, 2, and 3 this time. And then they give you 10, 8, and 2, 12. And then it turns out that 12 plus 8 is 20, which is half of it. Notice that you don't have to have the equal number, right? This time, even though there's 6 numbers, your set contains only 2 things. Okay, so basically the game is this. I give you a n, which is like I don't know, 10, let's say. You give me 10 numbers, different numbers. Based on that, I give you 10 other numbers. And from these 20 numbers, you have to pick out some subset that sums up to half the total. What are the constraints? There are at most 100 cases. You have at most 100 numbers. Every number that you get is at most from 1 to 1 billion. And none of the numbers are exactly the same. And the judge will choose BI such that the sum of all 2n integers is even. Okay, this is a little bit weird. So you have to give the judges some numbers, A1 up to AN, all of them are different, before you know anything, right? Other than the fact that you know there are n numbers. You don't know anything about what the judges' numbers are. So you send this, and then you receive a bunch of other numbers. They are guaranteed to be different than what you have. And then based on that, you have to find a subset of all of these things, of the 2n numbers, summing to half the total. Okay, Marcus, what do you want to say?
Sorry. So just to verify, this will always be possible, right? Like they'll never give you numbers that don't sum to a, or sorry, that you can't split into subsets. That would
Okay,
work,
so the
right?
only thing they tell you, the only thing that they tell you in the problem statement is that they will always make sure that the sum, the BIs that they give you will be that such that the sum of all the numbers, the ones that they give you plus the numbers that you chose, always add up to an even number. Okay, now they did not tell you that that means it's always possible. On the other hand, they didn't tell you what to do when it's not possible. Now, this was the state of affairs at the beginning of the contest. And then at some point during the contest, they added this one single line, which actually by the time they added this, I was already done. So what does it say? It says that it can be shown that given the limits of this problem, you can there's a sequence that if you choose this A1 up to AN correctly, then any sequence B1 up to BN that they can give you will result in a set of 2n integers that can be separated into 2 subsets with equal sum. Actually, that's not that's assuming it's not any sequence B1 to Bn, but any sequence so that when you add them all up, it's even. But anyway, yeah, by the time they posted this clarification, I was already done. I already knew that this is true because of the choice of AI that I chose.
Okay,
So
thank
anyway.
you. Yeah, because if they give you the numbers in a response to your own number, then it would make the question a lot easier, right?
Maybe. You mean if they give you the number first?
No. I just meant that if like you gave you numbers and then they gave you numbers such that the result was always possible, then the question would be a lot easier.
Well, if it's not possible, then it's impossible. You can't even do it, right? Anyway, I don't know if it's any easier even if they give you problems that are always possible, because you still have a bunch of numbers, up to 100 of them. You still have to figure out which subset to choose, because you cannot try all possible subsets. All possible subsets would be 2 to the n, which is way too big. 2 to the 100 is hopeless. Okay. Okay, so first of all, before I say anything more, any other questions about what this problem is about, or anything else? Okay, so now, your question was a good one, is it always possible? And I think that they were actually kind of nice for some reason. I didn't know why. Because at the beginning of the contest, when this problem was first posed, this line was not there. And then at some point, maybe a lot of people asked, and then some asked if it's guaranteed to be possible, and then they decided to post this in the middle of a contest. Usually, if I was a judge, I wouldn't post this, because certainly from the problem statement, if you know what's going on, it's possible to actually deduce this fact. But anyway, why? So let's say, how do I say that I can deduce this fact? How do I choose these numbers? Basically, I'm choosing them blind. I have absolutely no idea what numbers are coming, right? I have to choose these numbers blind so that no matter what other numbers you give me, I will somehow be able to use these numbers to add them up to something that I want, whatever that happened to be. Right, so this is a little bit tricky. I have to somehow pick a very, I don't know, friendly sequence that allows me to get whatever I want. Right, so what do I mean by getting whatever I want? I can add A1, A2, any subset of these. Okay, plus, or maybe I decide not to use it. So another way to think about it is that I have a, I guess you can say, B1, B2, up to Bn, where Bi, it's either 0 or 1. If it's 0, it means I don't use it. If it's 1, it means I use it. And I want to be able to say that by choosing Bi appropriately, whether it's 0 or 1, I will be able to add what, get a result of whatever I want. Does that kind of make sense what I'm trying to do? Maybe you don't see where I'm going yet. Okay, so now, when have you seen anything like this before, where you're trying to add a bunch of things? Either you add some, or you can say something times 0 or something times 1, and you can somehow get any number you want. If you were to call these 1, 2, 4, 8, 16, 2 to the n minus 1, if you do it like this, then you're essentially looking at the binary representation of a number. So if your AIs are just powers of 2s, okay, so 1, 2, 4, etc., then any number that you want up to the correct number, up to n digits, right, can be represented by basically a sum of these powers of 2 using the binary representation of the number. So even if I don't know what the number is, let's say I want, I don't know, 13. Well, 13 in binary is 1 plus 4 plus 8. Right? So if I want to form a sum 13, if I have the right set of power of 2, I will always be able to do it. Does that make sense? Yes, Marcus?
But say n was equal to 2, so you get to choose 2 numbers and they get to choose 2 numbers, right?
Yeah, okay. Okay, fine.
So what if they just gave you like the number 1 and the number like 8,770?
Okay,
then
hang on. Okay, so now first, let's say you just have 2 numbers. So you give 1 and 2. This is your set. And then you're telling me that they give what?
Well, let's say that they give you 3 and
Okay,
7,770.
but wait. Okay, let's read this problem again. They tell you that n is always 100. You cannot have smaller than that. Okay, so even though, okay, so in the actual sample interaction, it allows you for n equals 3, but actually, that's just for illustration because they don't want to show you what no, it says notice that the value of n here does not conform to the limits of the test sets and is used to simplify the example only. So you will always be given 100.
Okay,
Okay.
my bad. Thank you.
Yeah, no, that's maybe I didn't say that. So you are always allowed to choose all the numbers 1, 2, 4, all the way up to. Now you can't go to 2 to 100. That's going to overflow. So we're going to say that we only go if you're using 1 billion up to, let's say, I don't know, 30, 32 or something like that. Okay, that's probably enough. Oh, wait, you have to do up to 1 billion. So it has to be 1 billion. It's like 2 to 30. I believe that's the biggest power of 2 that you can have. That's still less than a billion. Okay, so you have 30 of these powers of 2s, and then what do you do with the rest of these 70 numbers that you have to provide? Just pick whatever number you want. Doesn't really matter. Just throw them in. The important thing is that with this set and whatever other numbers you throw in, you will always be able to represent any numbers that's from 1 all the way up to 2 to the 31 minus 1. Basically using binary representation of stuff. Okay, so this would allow you to go to represent any sum in the range from 1 to 2 to the 31 minus 1. So any number in this range, you can use the binary expansion to figure out which of these powers of 2s you have there. Okay, so that's the first insight. Does that make sense? So what is the more of the story? This part actually came to me quite quickly because I have to figure out something that works no matter what numbers you give me, and then sort of the only thing that I can think of was binary expansion of numbers. Then because either you take a number, you don't take a number, so that's binary digits, and that translates directly to binary representation of a number you're trying to form. And you can always, if you pick these numbers, you can always form a sum in this range. But now you have a different problem because the numbers that they give you are all between 1 to 1 billion. Hi, am I still here?
You just came back.
Okay, for some reason my internet of the whole house just dropped for a little bit. Okay, so where was I need to share my screen again. Okay. So my screen here. Okay, so what I was trying to say was that the numbers that they give you are between 1 and 1 billion. So are the numbers that you give. There are 100 of them that they give you. So altogether, there are 200 of them. So the total sum can be at most 200 times 1 billion, right? Every number can be up to 1 billion. There are 200 of them, is at most this much. So the half that you're looking for is at most 100 times 10 to the 9, which it's problematic. Why is it problematic? Because I told you that with this powers of 2s, I can give you any sum in this range, but this range is way too big. It's not big. This range is not big enough to cover the maximum half. So what do we do? Well, it's actually relatively simple. You have all these numbers. So you have your powers of 2s. And then you have the rest of these numbers. Just go put X. Okay, so I have a total and I have a half, right? The total is the sum of everything and the half is half of that. If the half it's in this range, I'm done because I can just now figure out the binary representation of that half and use the appropriate power of 2 to make it up. What if the half is too big? Well, if half is too big, I'm just going to grab one of these numbers and put it into here. Every time I grab one of these numbers, it's going to get smaller. The half, what I need to still make up is going to be smaller. I'm just going to keep picking them until eventually either half is equal to 0 or half has to be in this range. And I know this is going to work because I'm going to just keep subtracting 10 to the 9, subtracting something that might be big, and keep on removing it. And this half is going to get smaller and smaller and smaller. And it can never, if it's bigger than 2 to the 31, if it's still bigger than or equal to 2 to the 31, by subtracting one of them, because each one of these is at most 10 to the 9, I can never accidentally give me a negative number. Because if the sum that if the half that I'm looking for is still bigger than 2 to the 31, then it's definitely still bigger than 10 to the 9, so I can get rid of some of it by moving it to the half. And then eventually, if I keep reducing the half, eventually it will be reduced to this range, and then I'm good. Okay, and I will always be able to reduce it to this range because at some point, if at some point we move all of these into the half, then I'll be left with that. I'll be left with this, and then for sure it will be in this range. So that's basically my strategy then of this problem. Yeah, let me just make sure you guys are still here. You still hear me?
Yes.
Okay. All right. Okay, so my code is actually not that bad. Okay, so again, same thing. Read the number of cases, call solve that many times. All right, so what does my solve do? So the first thing I do is I read in the number of integers, which is always 100, but I have to read it anyway. Then I'm going to come up with my A. So I'm going to have A, n numbers in my array, in my vector A. I'm using 64-bit integers just in case. I don't think I need to, but I just wanted to be sure that I have no overflow. So what am I doing? The first thing I'm going to do is I'm going to initialize the first 30 elements to be basically 2 to the whatever, 2 to the 2 to the 1 to the 2 and so on. And this is a left bit shift. So if you have never seen this before, if you take a number and do a double arrow like this to the left, that means it's a left bit shift. And left bit shift basically means multiplied by power of 2 in this way. So if I is 0, then it's just 1. If I is 1, then it'll be 1. The binary number will be 1 0, so that's 2. If I is 2, then it will be 1 0 0, so that's 4, etc. And basically, if you're not familiar with this, if you have a decimal number, whatever number you have, and you stick zeros to the right of it, you're basically multiplying by a power of 10. So in base 2 is the same. If you stick zeros to the right of things, you're multiplying by powers of 2. So the first part basically just said the first part of the array is just powers of 2s. And then the second part here, I didn't even really care how I do it. It's not very efficient, but basically I just loop through all these numbers, 3, 4, 5, 6, 7, etc. As long as it's not already in the array, I add it. So basically this fills in the rest of it. 3, 5, 6, 7, all the non-powers of 2 until I have enough. Okay. Anyway, this is how I do it. It doesn't really matter. As the main thing is you don't want duplicates, and that's how I make sure there are no duplicates. This part I just print out my A, So this is my powers of 2 plus a bunch of other numbers. And then I read your numbers from the judges. And now the first thing that I'm going to do is I'm going to find the total. So accumulate is an STL function that allows you to basically sum up all the elements in an array. So I sum up all the elements in A, sum up all the elements in B, add them together, make sure that it's actually even. They guarantee that it's even. So it should always be even. And if it's not, then something horrible has gone wrong. So my program will crash. I guess this is just, this is not really necessary, but it's good practice, because if the judgment comes back as crash instead of wrong answer, then you know that maybe something here is wrong. Okay, so now that I have this, figure out the total and the half. So now I know what I'm trying to aim for is the half. And then here I basically, so this is a little, I don't know if it's really necessary, but I want to keep A just to be the power of 2. So I basically move everything that's not power of 2 to B. Okay, why? I guess I just makes it easier for me to think about the fact that A is always the powers of 2s and then B is the other stuff. So now what? So here, while half, whatever I'm shooting for, the number that I'm shooting for, it's bigger than 2 times the largest power of 2. So that's basically the largest number that you can form. It's the largest power of 2 minus 1. So my largest power of 2, it's 2 to the 30. Then the largest number I can form in binary is 2 to the 30 times 2 minus 1. So if a half is too big, then what am I going to do? I'm just going to use the I'm just going to pick one of the values from B. And then I'm going to remove it and print it. Okay. And I want to make sure that I pick one. If I manage to pick one that's bigger than half, then I don't use it. Okay, that's, I think, so I'm just an extra check just to make sure. And then when I exit this loop, I know that the number I have in half will be expressible as power of 2s, sum of power of 2s. So then this is just a very standard, well, I don't know if it's standard, but I didn't even bother looking at AI. This is just a binary to, in decimal to binary conversion. So while it's bigger than, the number is bigger than 0, if the lowest bit, it's odd, it's 1, then it's an odd number. So this is a bitwise operation. It checks if the lowest bit is 1, because a number that's odd will have the least significant bit 1 and least significant bit 0 if it's even. So this checks if the least significant bit is odd, and if so, then I print the corresponding power of 2. And then in the next iteration, I need to basically divide everything by 2, divide a half by 2 to get rid of that least significant bit. I need to make my power of 2 times more. So that's how I do it. And that's it. So this is a, I don't know if you call it standard binary into a binary conversion routine. So anyway, that's the problem. What is the, I mean, this is definitely more advanced. But I think the most important thing to realize sometimes is if you need to form a sum of some kind and you don't know what the sum might be, but you're allowed to choose what you're allowed to add, then usually powers of 2s will allow you to basically make up any numbers in a particular range. That's the main thing to learn from this, I guess. Now let's see what the analysis says. I have no idea what they did because I already did it. I didn't care what they say. Okay, they say a lot of stuff. In this problem, we first pick half of the input, then the judge picks the other half, blah, blah, blah. This means that we have to be really strategic on how we pick the inputs. We only get to provide half our numbers, so it might be best to first see how good of a split we can do with using just provide numbers, and only afterward come up the numbers. Okay, blah, blah, blah. So after we finish sorting out the judge's input, we know the difference between the two subsets is at most 10 to the 9. Okay, so they decide to split the judge's input into sort of two equal subsets to as equal as possible, and then decide to basically put the power, basically do a binary expansion of the difference or something like that. Anyway, that's kind of, oh, all right. Okay, so I think I made a mistake here. I said 2 to the 30 is the largest power of 2 that's less than 1 billion. It's actually 2 to the 29. So it should be 2 to the 29 is the largest power of 2, not 2 to the 30. That fits in under 1 billion. Otherwise, I guess it's their approach is a little bit different than mine, but more or less it's not that different. The main thing is powers of 2s. Okay. Let's look at the last one. I don't know how much we will say about the last one, but the last one, I solved the really small sample case. I actually failed on the test case 1. Then I passed the visible test, and then the temp basically it was memory limit exceeded. So I wrote this algorithm because I didn't really feel like solving the hard problem, so I just did an algorithm that was good enough for the medium, the test set 1, and I knew it wasn't going to be good enough for the big case. So anyway, let's read the problem, and then we'll see what we can think about. Okay, you're following a prescribed training for weightlifting. The training consists of a series of exercises that you must do in order. Each exercise requires a specific set of weights to be placed on the machine. There are W types of different weights. For example, an exercise may require 3 weights of type A and 1 weight of type B, while the next one requires 2 weights each of types A, C, and D. So they draw some pictures that shows you that. The weights are placed on the machine as a stack. Formally, with a single operation, you can either add a new weight of any type to the top, or remove the weight that is currently at the top. Okay, so you can only get rid of the top or put things at the top. You can load the weights for each exercise onto the machine stack in any order, right? So if you want 3 A's and 1 B, you can put it like this, or you can put the B on top and 3 A's on the bottom, or you can put the B on the bottom and the A on the top, or whatever. It's up to you. So if you place the weights of type B at the bottom in the first exercise of the example above, you'll have to take all the weights off before putting on the weights for the second exercise, right? Because if the B is on the very bottom, you need to remove the B to get to the next exercise. You must remove everything. Whereas in this configuration here, you have to remove the top A and the top B, but you can leave the last 2 A alone. So on the other hand, if you place the weights of type B third from the bottom, you can leave 2 of the weights of type A on the bottom of the stack to be part of the next exercise set, saving you some time. Given the amounts of weights of each type needed for each exercise, find the minimum number of operations needed to do them all. You must complete the exercises in the order given. The machine stack starts out empty, and you must leave it empty after you finish all your exercise. Okay, so basically, if these are the 2 exercises you have to do, you want to load your first set of exercises like this, for example, with the 2A on the bottom. Then to transition to the second exercise, you remove the top 2 plates. Then you put 4 more weights on top. And then at the end, you take all 6 weights off. And that's the best way. It means that you don't have to move the bottom 2. If you do it in other ways, then you might have to move more. Okay. So the first line of the input gives you the number of test cases. Each test case starts with two numbers, E and W. E is the number of exercises and W is the number of types of weights. Weight types are numbered between 1 and W. Then E lines follow. The ith of these lines contains W, blah, 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 representing that the ith exercise requires exactly that many weights of type J. Okay, so maybe it's easier if I just look at this. So here, let's look at the second case. You have two exercises, 3 weight types. The first exercise, you need 1 of type A, 2 of type B, 1 of type C. And then the second exercise, you need 1 of type, or 2 of type A, 1 of type B, and 2 of type C. And then you have to figure out how to move these weights from one exercise to another, and what is the minimum number of plates you have to move. For the small case, there are at most 10 exercises, and each exercise, there are only at most 3 different types of weights. And for each exercise, you're required at most 3 of each type. The second case is everything is much bigger. Everything is up to 100. You can have 100 exercises, 100 different types of weights, and each exercise can require at most 100 of each type of weight. Okay, so I look at this when I was doing this problem. I didn't know how to do test set 2 right away, and I knew how to do test set 1 because it's small enough. And then I said to myself, I'm just going to do it, and then if I can figure out anything better, I'll come back and try to do the hidden set. And by the time I kind of know what I was supposed to do, it was like 15 minutes left and I didn't have any time to code. And I didn't really work out all the details anyway. Anyway, so what is this small test case about? There are at most 3 types of weights, and each exercise can use at most 3 weights. So you can kind of do a quick estimate. How many different stack configurations there can be for an exercise? Right, so I have at most, so I'm just going to assume that everything is the max. So I have 3 different weights, each one for that exercise. For that weight, it's the most 3. And if I were to say, well, what can a stack of weights look like? Maybe it looks like this. Basically, there's 3 B's, 3 A's, and 3 C's in some order. And every time I switch something, that's a different configuration. Like this, right? And basically what I'm looking at is a permutation of a permutation of at most 9 objects, but with repetitions. Right? So 9 objects, 9 factorial, but then divide by 3 factorial because each of them can be repeated this many times. So this is, I'll just write something like roughly 3,608,000 or something like that. And then divide by 6 cubed. This is roughly 216. Maybe it's exactly. So I'm just going to kind of round it to 200. So let's just kind of round it. Ballpark 2,000 different configurations for each stack of weights. Okay, for each exercise, I can load it in roughly 2,000 ways. Okay, it's an overestimate, but that's not important. The important thing is that I have an estimate of some sort, and it's not that big. So now what am I going to do? If I have all these different stack configurations. One way to think about it is that I have exercises. Exercise 1, 2, 3, up to 10 exercises. And then down this way, I have the stack configuration. Up to, I don't know, let's just number them. It doesn't really, I don't even have to number them, but up to, let's say 2000 of them. And I can think of each of these as a node in a graph to represent that I'm in a certain exercise and I've decided that I'm going to load my weights in a particular way. So this is a graph. It has basically 10 columns, and maybe it doesn't even have to be the same number of rows in each column, because there could be a different number of weights and then different configuration of different types of weights used and so on and so forth. But what I can do is I can say that for each one of these, let's say I'm in this configuration, I can figure out how to get to every other configuration to the next stack. And how do I do this? So let's say this 2 is something like A, B, C, B, A. And this next one, it's, I don't know, C, A, B, B, like this. It doesn't even have the same number. What I do is very simple. I just scan from bottom up, and however many I have, those are the ones I can keep. These ones I have to take off. These ones I have to put on. So the answer is 7. I need 7 to move from this configuration to the other configuration. I just look at how many characters or how many types are the same at the very beginning, the bottom of the stack. We move them. Whatever is left are the ones that I must remove and add. And I'll just basically have a graph where every edge, there'll be a lot of edges. Okay, there'll be edges everywhere from one layer to the next. It'll look very messy on my drawing, but you can just construct this graph and you can figure out the edge weights of everything. And then what do? You basically can run, and then you have an empty stack at the beginning. You figure out how you get to from empty to that. It's really simple, because if you need 5 weights, then it's exactly 5. And then you also have an empty here. Same thing. And now you just run a shortest path algorithm of any kind. In fact, because this graph is a direct acyclic graph, you can even do something simpler with dynamic programming and work backwards and say, from each node, we cursively say, you know, what is the best cost from this node. And if you remember what the answer is, so you don't compute it over and over again recursively, this is going to be really fast. And that's basically the way to solve the easier problem, the smaller set. And you know, why did I do this and not think about the other one? Well, first of all, partly because I didn't know how to do it until the end. And then the other part was I was also watching the scoreboard during the contest, and I see that if I got that, it probably would be enough to get me through to the next round. So that's why I just decided to sit down and code this one to make sure that I move on the next one, and then I think about what to do for the harder set. Does that make sense?
Yep.
Now, yeah, I guess I don't know if I want to say anything about the harder sets. Let me say one thing, and then this was something that I noticed almost right away, but it took me a long time to kind of realize what I'm supposed to do with it. So let's say that exercise 1, you need, so exercise 1, 2, and 3. Let's just say you have 3 4 exercises, and then the weight types. Weight type, you have A, B, C, D. Okay, and then exercise 1, let's say you need, I don't know, 1 of this type, A type, and 2 of this one, and 1 and 4, and then maybe this one you need 3 and 1 and 0 and 2, and maybe C, you need C, 2, 4, 3 and 2, and maybe this one you need 5, 7, 4 and 6. Okay, so I'm just randomly making these things up. So exercise 1, you need 1 of type A, 3 of type B, 2 of type C, 5 of type D, and so on. Now, can you tell me what do you want? What do you think you should put on the bottom of the machine? And the very first exercise. Does anybody have any intuition about what might be a good? If you look at the minimum of each row, what it tells you is that every exercise that you have here, you need what? You need at least 1 A. You don't need B's. Well, some needs B, but not everybody needs B. Everybody needs at least 2 C's, and everybody needs at least 4 D's. Agree? And if these things are the ones that are always needed, you want to put them on the bottom right away. Why? Why do we want to put the bottom right away?
Because they won't move, right?
Because you don't want them to move. Yeah. They never need to move until the very end. Okay. These are always needed. So you put them in there in the bottom. You don't have to worry about moving them. And that saves you a lot of time, right? And you know that you cannot include, if you include anything more, then those anything more will have to be moved at some point. Okay, so that's the first observation, is that if you take the minimum of everything, yeah, of each type of weights across all exercises, okay, then what do we know is that you should put them in the very bottom, because now you don't have to move them at all from one exercise to the next. So that's the first, I guess the first observation. So these you put on the bottom, you do all your exercises, and then you move them at the very end. Make sense? Now the question is, what about the rest of these things? Because it's not that you do the minimum and then you're done, right? You have a lot of other things that it's not the minimum. Well, if you look across exercise 1, 2, 3, and 4, you're going to put your minimums here. You're never going to touch them. This is what you put in here. But at some point, you're going to put some stuff in, you're going to put some other stuff in, you're going to put, and so on. Maybe then you say, well, okay, what if I look at just these 2 exercises? Okay. Okay, maybe let me say, if you have a bunch of exercises, I'll just draw them in a lot of boxes here, because you can have up to here. At some point, maybe you just say, let's decide to cut here. and I look at the minimum here, and those are the ones that I don't have to move. And what would I do with those minimum? I would load them in at the beginning of this set of 4, and then I will unload that minimum at the set of 4. Because the minimum for the next group might be different. And where do I actually cut this? I don't know. I try all of them. And then I just kind of recursively do things. Okay, this might be a little bit, if you're not used to thinking about this way, this might be a little bit advanced. And in fact, I guess it's too advanced for me to figure out during the actual contest. I kind of know this is what I was supposed to do, but then I kind of ran out of time. So basically, this is how you're supposed to solve this for the larger problem. It's by saying, if you know recursively, how do you get the best cost for a particular subset, or I should say contiguous subsequence of exercises, then you do things recursively by basically taking out the minimum across the set, and then basically just recursively deciding how to split it into 2 halves and try all possible ways of splitting in 2 halves. Okay, so that's kind of if you've seen that kind of thing before, it's a dynamic programming that's kind of has an n-cube complexity. But if you have never seen this before, then of course you don't necessarily know what I'm talking about. If you have taken 3620, you might have seen a problem called optimal matrix multiplication. Has anybody seen that? Not everybody teaches that problem, but some people do. And it's in the textbook, in many textbooks. Anybody?
Is that the thing where like you look at all the, because multiplication is commutative and you look at all the different ways you can
Yeah,
multiply the matrices
right. And then
and
you
then
want to
find the
see
best one.
exactly. And this is in that kind of way. You're kind of looking at all the different ways you can partition a range into two sub ranges and then recursively figure it out. It's the same kind of approach, I guess. Okay, anyway, let me stop the share. It's now running to